All right, you guys, we're going to start talking about geologic time. But before we do that, we're going to actually talk about what we had in place before we had modern geology. So what we had before modern geology was something called catastrophism. Basically, they thought the Earth was a lot younger than it was, and we had Bishop Ussher to thank for that. Bishop Ussher was a biblical scholar, so he took the Bible and he figured going back from his generation to Adam and Eve and who begat whom and generation times and stuff like that, that he said the Earth was created in 4004 BC. And to be exact, October 23rd at 9 a.m. Okay, it sounds a little crazy to me. But with the Earth being so young, you had to explain everything you saw on the surface of the Earth in that short period of time. And so that's where catastrophism came about. Now, you guys, all fossils came from Noah's flood, according to Bishop Ussher. What else? If you saw something like the Grand Canyon, which took, I don't know, 10 million years to carve, you had to say that that happened pretty quickly, or the Himalayas shot up pretty quickly. It would have been a scary Earth if we had a catastrophic Earth. I'd be afraid to take a walk because I might all of a sudden be shot up to amazing heights or fall down to the bottom of a very deep canyon that immediately opened up. So, it took a long time to get over this bias caused by, religion with blinders. And we have James Hutton to thank for that. And James Hutton is kind of the father of modern geology. And he was rich, and instead of, being debaucherous and drinking too much and chasing little girls or something, he spent his time being kind of a Renaissance man and just observing a lot, hiking a lot, being outdoors, and thinking about things, and was highly educated. And he came up with pretty much the main principle to start modern geology called uniformitarianism. He took a big risk. In the past, people who had done things like this that kind of spit in the eye of the church were excommunicated, maybe, executed, were shunned by people. And he was rich enough that, nobody would publish his stuff, so he bought a publishing place and he published himself. And what his principle of uniformitarianism says is that the present is the key to the past. Now, he was a pretty old man for that time, and he'd spent his whole life, along the shores of Scotland, hiking up and down from the seashore to the tops of the mountains there. And he had noticed that, the mountains didn't get any smaller in his life. And he would hike along the rivers, and he'd notice that pieces of the rock from the top of the mountain would be broken up and carried along in the streams. And he noticed it got deposited, and he went down to the shoreline, and he saw very fine-grained sediments being deposited, and again, deposited slowly over his lifetime. He also saw the rocks that made up the shore were old sedimentary rocks, and figured, they're pieces of sediment, and it was kind of, they were formed probably very similar to how those mountains were breaking down and being carried down by the streams and deposited. And he said, you know what, this Earth is a lot older than it seems, or that the religious people would have you believe. And so the present is the key to the past. Things that are happening today happened in the past and about the same rates. Now, he wasn't completely right. He said the Earth had to be millions of years old. And we know now that it's actually billions of years old. But he put us on the right track. And when he didn't get his head chopped off or, in any big trouble, all the closet geologists came out and, said what they were thinking. All right, we're going to start by talking about something called relative dating. Now, if you guys grab your geologic time scale, what you're going to see is a bunch of weird names and a bunch of numbers. I want you to mentally take those numbers off. Those numbers are based on radiometric dating, and radiometric dating didn't come about until about 60 years ago. So all those names were put in order according to their sequence of events, who's older, who's younger, according to the relative dating principles. Now, when I go in the field, I can't take a pocket, radiometric dating machine. It's just not done. And so I need to be able to put the rocks in order according to certain, logical principles. And so what we're going to do is we're going to go through that and learn about these logical principles. Okay, they still work today. I use them every time I go out in the field, and they're pretty easy to learn because most of them are very logical. All right, grab your sheet that has the relative dating and basic geological principles. And so there's some pictures there to go along. And pretty much the most basic one and very important is the principle of superposition. That if you see a stack of fairly undisturbed rocks, you can assume that the oldest ones are on bottom with the younger ones on top. If you look at the picture on the handout, you can see A, B, C, D, E. Now A has to be older than B because for for B to be placed on top of A had to have been there, and so forth and so on. So you could say A was the oldest and E was the youngest in that stack of rocks. You guys, it's so logical, but it really is pretty amazing that it took kind of, the barn door opening, all the closet geologists come running out, back in the late 1700s, early 1800s. All right, another important one is that all rocks or sedimentary rocks at least, were originally laid down horizontally. Now, that was a big surprise for me. I grew up in Santa Barbara, and the mountains are all sedimentary. Can't think of one example of horizontal sedimentary rocks. They're all tilted. But you know what? They were originally horizontal, and the fact that they're tilted tells me that they've been through some major tectonic event. Big arrows, okay? Arrows coming together, pulling apart, and sliding by each other. That's what can tilt rocks and break up, the layers and fold them and things like that. But originally, sedimentary rocks were laid down in a big basin, usually with lots of water involved, and they're laid down flat. So original horizontality. Now, you don't have to know the name. Nicholas Stena was actually a Jesuit priest. And so, there's religion without blinkers, and I have nothing but the most respect for religion without blinkers. All right, now here's just the top couple of layers of the Grand Canyon. I hope you all get a chance to go see the Grand Canyon. And hopefully this class will make you appreciate a little bit more about the incredible power of being able to kind of look at it and interpret it. Now, because of the principle of original horizontality, we know that the Supai group there on the bottom of this picture is older than the Hermit Shale. And the Hermit Shale is older than the Coconino Sandstone. And the Coconino Sandstone is older than the Toroweap. The Kaibab's the youngest on this section, and the Kaibab's actually pretty old. It's Permian in age, and boy, that's about 250 million years old. And so it's kind of funny, if you're standing on that side of the Grand Canyon, on 250 million year old rocks. And I always ask, where did they go? Where did the rocks that are on top go? And if you come on a field trip with me and we go out there, I can show you. Very cool rocks. Okay, the principle of original horizontality is kind of shocking, you guys. These are old rocks, and for the most part, they are still horizontal. Typically, continental rocks get messed up if they're old because remember all the fender benders we talked about in the plate tectonics section. All right, another really important one. You guys, superposition and cross-cutting relations are probably the most important, but let's talk about lateral continuity. Now, if you are following a really thick sedimentary bed, okay, as a formation, a mappable unit of rocks like we saw in that last slide, and all of a sudden it stops and it's still really fat, okay, you know that it's been offset because it should be laterally continuous. Sedimentary rocks are laid down in basins, and basically basins eventually taper off. Even the ocean edges taper off. And so what I would expect if I'm following a really fat unit is for it to get thinner and thinner and thinner as I move out until I finally find its edge. But if it just stops abruptly, okay, you've got something that's messed with it, and it's probably a fault, and we'll see an example of that later. All right, and then cross-cutting relations. You guys, superposition, cross-cutting relations, these are the two I use the most. If a feature like an igneous dike or a fault cuts a pre-existing rock, that rock that it's cutting must be older. That feature that's doing the cutting must be younger. Look at your diagram. There's another picture in your handout, and you can see again a stack of rocks A, B, C, D, E. Then what you see is a granite intrusion called G, a dike. A dike is just a long, thin, that happens to be a granitic one. Igneous intrusion usually follows a crack or something. And then H is a darker, a mafic igneous intrusion, and that's also a dike. Now, H is the youngest of all because it cuts everything. So we can use superposition, and when I do things like this, I always start at the bottom. You got to start at the bottom. You got to go with who started, who's the oldest. You got to start with the oldest rock unit, and then move yourself up. So A is the oldest, then B, then C, then D, then E. Okay, then F, because F cuts all of those other units, and then F is cut by G, okay, and then the youngest of all is H. Okay, so it's pretty powerful, and like I said, we're going to get some practice doing this, and you guys are going to mainly be using superposition and cross-cutting relations. All right, so it's kind of easier to show you a picture. Now, you guys, in your weekly folder, I have the animation that will take you through this. This is actually really, really easy. On the left-hand side, see the fault? And check out the horizontal layers and notice how they're offset or cut. And remember what I said about lateral continuity. If you're following that that horizontal kind of brownish layer that the arrow, the head that says fault A hits, you're following it along, and boom, it abruptly stops. You look up, you look down, you look left, you look right, because that's how a fault can move, and that's actually a fault, and you can see it's offset quite a few layers. But look at that kind of top gray, pebbly looking layer. It says a conglomerate. It is not offset, so that fault went extinct, and so you would know that the fault is younger than all of those features that it cuts, but the conglomerate sits on top and is not cut, so the conglomerate has to be younger. Okay, you can see the dikes in there that are labeled. You can see a fault on the other side, and you know that fault was no longer active when the batholith cut it, and then later the dike. And then we haven't really talked about sills. Dikes are not going with the bedding planes, or they're not parallel to those horizontal layers, whereas a sill is horizontal or parallel to those horizontal layers. And the youngest thing of all is dike A. Notice it cuts everything. So that animation, if you can see it, it's really, really going to help you, because you guys are going to actually put this into practice. All right, so watch that movie. I can't say it's, you see it and you look at your picture and you're like, okay, I get it. All right, now this is actually taken right down the street from the Sierra College Rockland campus. And these are dikes, and can you guys guess which one's older? There's a horizontal one and there is a vertical one. Which one's older and which one's younger? Okay, think about that for a second. Who cuts whom? Okay, yeah, the horizontal one is the younger. It is cutting through the vertical dike, okay? All right, principle of inclusions. When you guys did your rock walk activity, they had a big piece of Sierra Nevada granite, and in it was what I call the big black blobs, the pieces of the pre-existing rock. That, remember, the granite was a magma. It intruded into pre-existing rocks. Pieces of the pre-existing rock fell into the magma. It didn't melt because it was higher temperature, and then the granite cooled surrounding it. So the rock on the inside has to be the older rock, because it had to have existed before the rock form that surrounds it. Now, actually, it's kind of interesting. The picture that's in your handout shows actually another rock that we can find locally, and it was also in that rock walk. We looked at, well, actually, it was the Lahar, the volcanic mud flow, and in that volcanic mud flow were pieces of granite that had actually worn out of the Sierra Nevada and then been mobilized with a volcanic mud flow. And the volcanic mud flow matrix, the ash stuff, was surrounding the granite cobbles. And you know the granite cobbles have to be older. They have to have pre-existed before they were surrounded by what became the volcanic mudflow material, or the lahar. So pretty cool. So xenoliths, inclusions, those are the same thing. So the principle of inclusion, the one that is surrounded, the one inside, the one that's surrounded by the other rock, has to be older. It had to pre-exist. All right, here is one of those big black blobs. This is taken right on Sierra College Boulevard and English Colony Way, if you guys know the Rockland area. And you can see that that rock, the black one, the blob, was pre-existing rock. It fell into the molten granite. It's higher temperature, so it didn't melt, and the granite solidified surrounding it. Okay, so yeah, it's older because it's surrounded by the granite. All right, now this is kind of fun. If you guys go up when the snow melts on Old Highway 40, just past the Sugar Bowl ski area, you'll go up and you have a great overlook of Donner Lake, and it's called McGlashan Point. And this part of this magma body, this pluton, was actually up at the top, nearest to where the country rock was, and you can see a lot of that pre-existing rock has fallen into here. And so it's actually, in some ways, it might be equal amounts inclusions and then the surrounding granite, but those inclusions are older. Pretty cool. All right, unconformities. I believe in your, yes, in your weekly folder there is a document you should print out so you can follow along, just that shows you the 3 different types of unconformities. Now, somewhere on Earth at all times, sedimentary rocks are being laid down, or all rock types. Let's just say all rocks are being formed somewhere. But there's no place on Earth that has a complete record of all 4.3 billion years of kind of layered Earth, or a little bit more than that maybe. We have 4.3 billion year old is our oldest rocks that we have. But there's no place that has that entire rock record. So we have to do something called jumping around. And I'll tell you a little bit. It's the fancy word is correlation, but we'll make it fun. Jump around. And so we're going to have to kind of run around and try to figure out how can we make a story about the complete stack of rocks, and what happened first and what happened next all the way to the youngest stuff. Now, because you're going to have missing rocks in certain sections, we call those unconformities. And unconformities are basically erosional areas, places where you've had erosion. Remember when we looked at the Grand Canyon and you're standing on top and I told you that, oh yeah, there's, you're standing on 250 million year old rocks, and I always look up and go, where are those other 250 million years worth of rocks? I can take you to another place not far away where that Kaibab limestone is on the bottom of the stack and the younger rocks are on top, and that's part of that jumping around thing. So, you could be missing a pretty significant amount of time, and I think later on I'll tell you a little bit about our local to Rockland example where we're missing about 120 million years of rock deposition. All right, there are three main types. There's an angular unconformity, and that's really easy to spot. There's what's called a disconformity, and this is a little more difficult to spot at times. And then a nonconformity, and we have a great nonconformity just down the road from the Rockland campus. So I'll talk about that too, and it's pretty easy to spot. All right, angular unconformity. You guys look at this picture. What's wrong with this picture? You've got horizontal layers on top, but oh my gosh, those are tilted layers on bottom. And so there's actually a line in there that represents the erosional surface, and it's that line where the tilted layers meets that very first horizontal layer. So when you see something like this, let me tell you the story. Those bottom layers were originally laid down horizontally in a basin. Okay? Then there was some sort of a tectonic activity, either arrows coming together, pulling apart, or sliding by each other, and those rocks were disturbed. They were tilted, and they were probably uplifted and eroded, and they were eroded down flat enough that now we are low enough, we're going to start laying more sediments, and rocks are going to form on top, and they're going to form horizontally. So that angular unconformity there, it's just a line, you guys. It's just, I could actually, too bad I don't have the ability to draw a straight line right where it is, but it's where those tilted rocks meet the horizontal rocks. And that is your angular unconformity, or your erosional surface. All right, so here's another little story. You lay down rocks originally horizontally. In this case, we have compression, and it folds the rocks. It uplifts. Big arrows make mountain ranges. It uplifts, and so we get erosion. Anything that sticks up is going to be eroded. Erodes down flat, or low, and then the sea comes in, and it just covers it with new flat horizontal layers. So that is how you get an angular unconformity. Now the rocks on the bottom could be tilted, they could be folded, but as long as they're not horizontal, that is an angular. If the two beds are meeting at an angle, that's an angular unconformity. All right, what happens if two layers are horizontal? How are you going to recognize it? So if your lower set is horizontal and your upper set is horizontal, this is called a disconformity. I've got a great picture. It's in the next slide or two. And so what's going on is that you've laid down rocks horizontally. They've been uplifted from some tectonic event, but they've been uplifted pretty horizontally, just kind of like the top part of the Grand Canyon. And then they're eroded down flat, and the deposition starts to happen on top. Now the first thing I always look for is the erosional surface. If you guys notice those bedding planes, kind of the cake layers, they're usually horizontal and they're usually pretty clean. And so if you find a big wiggly line that represents an erosional surface, I'll show you a picture, you're looking at a disconformity. Now the other thing you can do is you can find a gap in the fossil record. Sedimentary rocks typically contain a lot of fossils. So right here is a great one in the southwest. You guys, I put with the white line. Look at the other layers. They're all, like the bedding planes are all horizontal. They're kind of laid down like a cake. But look at the surface that I've kind of drawn a little white line over to really point out that's the erosional surface. And where the rocks are a little softer, it's eroded a little bit more. Where the rocks were a little bit more resistant, it's less eroded. And that's why it's not a flat line like the other ones. It's a wiggly, squiggly line. That represents erosion, so you have a disconformity. All right, the second way that I usually find it is I find the missing fossils. Now, what we have here are some cephalopods that have evolved, and it's kind of like they're relatives of squids and octopus and nautiluses, and they actually evolved over time from a straight variety, and then over time it coils to something that's like a nautilus. And so if you're collecting fossils and you go straight from a straight variety to a coiled variety, you know you're missing a lot of time. Now, this is as obvious as, this is very obvious to a paleontologist, but let me think about something that would be more obvious, an example. So if you see that where it's labeled on the right-hand side, disconformity, if you found a dinosaur in that layer right below the big black line, okay, but then right above the big black line, you found a hominid. Okay, dinosaurs and hominids did not live at all close together. There's at least 60 million years separating them. And you'd be like, what? How can these guys be laid down so closely? They weren't. The inner, spaced rocks have been eroded away because there should be a lot more fossils between dinosaurs and early hominids. Okay. All right, you guys, this is a little more complex than it has to be. But what they're trying to do is show you how a nonconformity would form. And so if you look at F, you can see high-grade metamorphic rocks and an igneous intrusion that basically created that metamorphism with non-messed up layered sedimentary rocks on top. And so you can see where they pointed that nonconformity in that entire line there where I guess that's probably schist. It's hard to see at this small scale. Schist and granite are in contact with that first kind of tan sedimentary layer would be my nonconformable surface. All right, so back to the Grand Canyon. You guys, you got to go to the Grand Canyon. If you get a chance, go, rafting down the inside. And when you're rafting, you're down there where it says Inner Gorge and the oldest stuff, and that's almost 2 billion years old. And so let me just kind of tell you what happened. You had the pre-existing rock that's going to become the Vishnu schist. The Zoroaster granite intruded into it and metamorphosed it. Okay, then that whole system, it was uplifted and eroded, and the Unkar group was laid down. Okay, then that was uplifted, tilted, and eroded, and the Tonto group was laid down. Now that was uplifted and eroded, and the Redwall limestone was laid down, and that was uplifted and eroded, and the Supai group was laid down. Now the Supai, Hermit, Coconino, Toroweep, and Kaibab are what we call conformable. They were all laid down together. But think about it, the Kaibab is young Permian, and so there is a lot of missing rocks, about 250 million years worth of missing rocks on top of that. So pretty darn cool. So the oldest would be the Vishnu schist, and the youngest in this would be my Kaibab limestone. Love this section. All right, let's talk about jumping around or correlating. And I gave you an example before. I can take you from the Grand Canyon where we're standing on the Kaibab limestone, and I can take you a couple of different places, and we can find the Kaibab limestone at the bottom of a stack of rocks, and we can find some of the younger rocks sticking on top of it. And we do that kind of by number one. Back in the old days, you walked it out or your horseback rode it out. Now we drive it out, you guys. So I could take you all over the Colorado Plateau area, and we could, drive out and make the entire stack of rocks for that area. It's pretty exciting. So physical continuity. Oh yeah, and the whole time that we're driving from the Grand Canyon, we'll be looking and we'll be seeing that Kaibab limestone the whole time. So that's the physical continuity. It's very easy to recognize once you recognize it. All right. Now, if you see rock types, you have to be a little careful of this because, you guys, there's certain rocks that just happen all the time. If you see a sandstone limestone shale and you're like, oh, there's a sandstone limestone shale at the Grand Canyon and there's one at the Santa Barbara coastline. No, they are separated by hundreds of millions of years. What you have to do is you have to look for something unusual in it, an ash layer, a coal bed, something like that. It has to be something unusual. An example, Zion. Zion National Park is sandstone that's cross-bedded. It was part of a huge dune system, and it's in Utah. Okay, if you go to Arizona, they call that unit something else, and if you go to Nevada, they call it something else too. But we can match all it's called the Nugget and the Aztec, but it's the Navajo formation. And so we can match them because it's a massive cross-bedded sandstone. And so those cross-bedding, so signs that it was laid down in a dune field, really help you. That's the unusual thing. All right, but the easiest thing to use is fossils. If you guys came on a field trip with me down to Death Valley, we would go someplace where we'd actually, outside of the park, maybe collect some trilobite fossils. And trilobites are extinct, and you'll learn about trilobites. And if we did that, and one of your friends that was having what would that be, a semester abroad in England, was like, oh yeah, I found a fossil. And you guys got together and it's like, oh my gosh, it's the exact same fossil. What's going on? You have just correlated across the ocean, you've just correlated that those rock units have to be the same age. So fossils are extremely, useful in that. All right, so just a little bit about fossils, and the good news is you guys don't have to tell me a bunch about the different types of fossils, but I want you to realize that there's a lot. Most of you know about petrified wood, and in fact, the Roseville area is a big source of petrified wood. Petrified means terrified. Okay, that wood didn't turn to stone because it was terrified. It's actually called, it should be permineralization or replacement. There's no wood left. Every molecule of organic material has been replaced by silica. It's just been replaced slowly enough and carefully enough that it's kind of looks like a piece of wood. Okay, there's molds and casts, and you guys, like if Bigfoot ran by, okay, I'd go get some plaster, and in his footprint, I would make a cast of his footprint. His footprint, when he ran by, left a mold, and I would fill that and make a cast of Bigfoot's footprints. And so you could have a mold or you could have a cast of a fossil. Okay, here are some casts of these ammonites, these coiled cephalopods. All right, carbonizations, I'll show you guys slides. Leaves make really good carbonizations. This is actually real carbon material, so this is the organic stuff. And, it happens in very fine-grained sediments like clays. You could have an impression. If you put your hand in some plaster and left an impression of your handprint, that would be, your impression. Preserved in amber, that got a lot of news with Jurassic Park. And yeah, we have lots of insects and even amphibians and reptiles and stuff preserved in amber. Amber is just fossilized tree sap. All right, here's a carbonization of a bee. You guys, we wouldn't know a whole bunch about bees if we didn't have this sort of fossilized data. Okay, here's an impression, although there is still some biological material we can pull off scales and the fine bones on fish. All right, there's something called trace fossils. I was showing you guys like body fossils, real fossils, and footprints. Unless the foot is stuck in the footprint, it is a trace fossil. Okay, fossilized dinosaur doo-doo, don't laugh, it's true. I have a friend that has the first PhD ever, and they laughed at her until she got a big paper or two. It's called biogeochemistry. And so yeah, there's fossilized dinosaur doo-doo. That's what she studied, and she could tell what the dinosaurs ate. Now, she also had the oldest known dung beetles, and she could see their burrows in the big herbivorous dinosaur poo-poo. Okay, and then there's these things called gastroliths. A lot of dinosaurs, you guys, my chickens when I was a kid, my chickens ate gravel. And a lot of dinosaurs either didn't have teeth or they had really poor teeth, and they're eating this very fibrous vegetation. And, they ate some stones and put it, it goes into their gizzard and it helps grind up this fibrous food, just like chickens today. And so when we find fully articulated skeletons of dinosaurs, we typically find this pile of beautiful rounded rocks in their stomachs for the herbivorous dinosaurs. So pretty cool. All right, here's just a footprint, and you see those around a lot. Okay, now you guys, back to what's really important. Luckily, not everything is fossilized. I would hate to go out and dig in my garden and just have the skeletons and fossils of every organism that ever lived. In fact, it's kind of like all the planets don't align all the time. It's pretty rare. It's kind of like that. All the planets have to align in that you have to have all these different things happen to be fossilized. You got to die if you want to, have a very good fossil. Preferably all the parts or most of the parts. It helps if that organism died in a basin or a low-lying area. It helps if they were rapidly buried. If they sit at the surface, scavengers are going to come and pull them apart, and they're going to rot and things like that. You guys think about what's the probability of a jellyfish being fossilized? It's not good, but we do have fossilized jellyfish, and that's because they were quickly covered with very fine-grained silt, clay sediments, okay? And what that does is it actually cuts out the oxygen. Anoxic is oxygen-free. If you have ever had anything rot in your refrigerator, it's rotting and getting stinky because of its oxygen. And if you can take the oxygen out of there, it typically doesn't rot, and that will help to preserve it. It might become like mummified or something. So, you've got to have fine-grained sediments if you're going to have any soft parts, and also anoxic or oxygen-free environments. Now, there's a star there where it says possession of hard parts. Hard parts evolved at the end of the Precambrian, the beginning of the Cambrian. So if you've got just a kind of a generic geologic timescale, not the one with all the pictures of the organisms. And there ought to be a big black line there. I'll go in and double check. If not, I'll make a video when I kind of explain this stuff and show you the big black line. And so the big black line is in between what's called the Proterozoic and the Paleozoic, or the Cambrian and the Hadrianian. And that represents where organisms evolved hard parts. Okay, the earliest part of the Cambrian. Before that, there were organisms, but they didn't have hard parts. So think about it, you guys. If you go out on a fossil dig with me, we're likely to find bones and teeth, hard parts. Until organisms evolved things like that in outer shells and for mollusks and for organisms that live in the ocean, your chance of being preserved, fossilized, was really poor. And so that was important. So that big black line and above, or the Precambrian, Cambrian boundary and above, we have a lot of information about it because organisms are much, much more likely to be preserved. All right, one last principle, the principle of fossil succession. You guys, William Strata Smith, his nickname was Strata, layers. He was a canal engineer. I've heard him called a ditch digger, but whatever. He was intelligent, and he dug canals and ditches and stuff like that all throughout the British Isles. And he started to realize that, hey, when I see this one layer, and I'll always see this other layer, and that other layer will always be above or below. So he understood superposition, and then he noticed, hey, fossils. And he noticed that they always occurred in certain order. And so he said that fossil organisms succeed one another in a definite and determinable order. Now, this is before Darwin and Wallace came up with the theory of evolution. So we need to add another name. Smith, Darwin, and Wallace are basically the fathers of evolution. So pretty darn cool. Fossils really tell us a lot. They are useful. All right, now you guys have a handout that kind of talks about fossils, and it's the geologic timescale with the organisms, pictures, and then these black lines. And if you're going to if you are out in the field and you're looking, for fossils, and you find what's called an index fossil, you practically kiss it, because if you find certain fossils, you know exactly how old your rocks are. And if you look at your handout, an example of that would be Olenellus. If you look at the very bottom left, Olenellus is one of those trilobites. And Olenellus, all the organisms on here were geographically widespread. Okay, but Olenellus, that little black line next to it, shows that he evolved and then went extinct pretty quickly. So existed for a short period of time. So if you find Olenellus, you know you're in the earliest Cambrian. So you would kiss the ground. But unfortunately, that's not what you typically find. Typically, you find one of the organisms that has a very long line. And what that does is that makes it a little bit more difficult. But don't despair, because if I've never been out where I've only found one fossil. Usually you find lots and lots of different organisms, and you can take all of their different black lines, even if they're not short, and figure out when they all coexisted. So when you go out and find a lot of different organisms, that's called a fossil assemblage. And we're going to actually go through, I made a movie, you guys, for the next slide. I'll kind of briefly explain it, but I've got a separate movie. And you've got to understand how to do this. There will be one of these on the exam. You have one as an in-class assignment. How to narrow it down and figure out when these organisms all coexisted. So this is the diagram that is in that movie. Please do watch it. I think I explained it pretty carefully. The one problem with this diagram is on the left-hand side should be a geologic timescale. At the very bottom is the Cambrian, all the way up to the very top would be today. And so this is the distribution. And look at those organisms. They all have pretty long lines. In this case, they're not black, they're white lines. Look at the scallop, you guys. You know, if you show me a fossil scallop, it lived, you know, scallops have been around for like 350 million years. I can't tell you how old the rock is if that's all you find. So we're going to go through and figure out how to use these fossils to narrow it down a lot more. All right, so once you watch the movie, you should be able to do your in-class assignment number 16. It's also in your folder, and here it is here too. All right, absolute dating. So we're ready to talk about radiometric dating. Now, you guys, this is a serious science. It's not something made up. It is, you know, repeatable. I can send something to one lab and send it to another lab, and they should come back with the exact same numbers. There are a lot of different radiometric isotopes. Remember, an isotope is an element with a varying number of neutrons, some of which of the isotopes are stable and some are unstable. The unstable ones are called radioisotopes or radioactive isotopes. Okay, radioactivity was discovered in the 19th century, and in fact, I got to push, you know, it was discovered by a woman in cohorts with men. Marie and Pierre Curie and Henry Becquerel discovered this, and they got Nobel Prizes in the early 1900s for discovering it. And so radioactive decay is the spontaneous breakdown of the nucleus. So before, we really spent a lot of time talking about the electron shells. Now we're going to actually look inside the nucleus, okay, and talk about the changes that happen. Now, radioactive decay releases energy. Remember, this is what heats the inside of the Earth. This is what powers nuclear power plants. And you know from nuclear power plants that if it's not contained and properly cared for, that it can be darn right dangerous. All right, we are going to have to review atomic structure again, and I will probably make a movie about this. I think that might be a wise idea. So in the nucleus, and this is where we're going to be concentrating, we have protons. Protons have a +1 charge. They have 1 atomic mass unit. Neutrons are neutral. They have 1 atomic mass units, they each weigh 1 atomic mass unit. And if you remember, electrons are in the electron shells. They're -1, and we ignored their mass because it takes 2,000 of them to equal the 1 atomic mass unit. Now, the one thing I didn't tell you before is what a neutron is. A neutron is a marriage between a proton and an electron. They're fused together, okay? And so it kind of makes sense. +1, -1, 0, okay, no charge. And then 1 atomic mass unit, basically 0 mass, you know, 1 atomic mass unit. So, you know, here's neutrons kind of uncovered. Now, it's kind of interesting, you guys. We're going to have a marriage and we're going to have a divorce when we start talking about different types of radioactive decay. All right, remember what atomic number is? If I ask you, hey, what's element number 8? And you say, oh, it's oxygen. Then you are telling me that, you know, it has 8 protons, and you're identifying the element, and that would be correct. So the number of protons is the atomic number. But the atomic mass, if I talk about radioisotopes, you don't talk about their atomic number, you talk about their mass. Uranium-238. You guys look on your periodic chart of the elements. There is no 238. You know, oxygen, there's oxygen-18 is the radioisotope. And you look, 18 is not oxygen. So, you know, understanding that's pretty important. Remember what the mass number is. It's the number of protons plus neutrons that live in that isotope's nucleus. And so an isotope is an element with a varying number of neutrons. So for instance, carbon. You and I have a lot of carbon in us. It's carbon-12. There's also carbon-13, and there's also the radioisotope carbon-14. It's carbon, so it has to have 6 protons, but the carbon that's in us has 6 neutrons. Carbon-13 has 7 neutrons, and carbon-14 has 8 neutrons. So that's where the atomic mass number comes from, protons plus neutrons. All right, so we said radioactive decay is spontaneous breakdown. Now, the parent is the radioactive element, and then the stable element that it creates is what's called the daughter element, okay, or the daughter product. Okay, so the daughter is the stable product that happens after the breakdown of the parent, and the parent is the radioisotope. All right, there are 3 different types of radioactivity or radioactive decay, and you are going to have to be able to name and briefly describe one of these for the exam. I'm going to make a movie. I'm going to draw you guys pictures and talk you through this. All right, alpha decay. An alpha particle is 2 protons and 2 neutrons. And when a radioactive isotope is unstable, its nucleus is unstable, one of the things it can do is shoot out 2 protons and 2 neutrons. Okay, so we are creating a new element because we're going to be -2 on the periodic chart of the elements. We've just lost 2 protons. And we're going to be 4 atomic mass units lighter. All right, beta decay is a divorce. It's very sad. A neutron in the nucleus is unstable. It's got an unhappy marriage. And so, you can't have a proton in the nucleus unless it's married. And so the proton, or you can't have an electron, I'm sorry, you can't. All right, the first type of radioactive decay is called alpha decay. The radioisotopes that go through this, their nucleus is unhappy, and what they're going to do is they're going to shoot out an alpha particle. And an alpha particle is 2 protons and 2 neutrons. If you shoot out 2 protons, you are now 2 less on the periodic chart of the elements. You've changed your atomic number. And if you shoot out 2 protons and 2 neutrons, you are 4 less in atomic mass. So you're lighter. So you do create a new element. All right, beta decay is a little sad. It's about a divorce. The marriage of that 1 neutron in the nucleus, or of a neutron in the nucleus, is just not going to work out. And so protons stay in the nucleus, electrons get shot out. So we shoot out an electron. Well, it's just an electron, so it doesn't change the mass, but we have changed the number of protons. We've just added a proton. And so what we've done is we've changed the element. We're actually up 1 on the periodic chart of the elements. All right, the third type is electron capture. This is a little happier note. This is a marriage. A proton in the nucleus is lonely. It wants to get married. And so the nucleus will capture an electron, it will fuse with a proton and become a neutron. And so we will create a new element and we will have lost a proton. So we are -1 on the periodic chart with actually no change in mass because, again, what came in is just an electron. All right, now this is a little bit of a better picture than the ones I'm going to draw in my movie for you. In the first one, you can see the protons are the blue circles and the red circles are the neutrons. And an alpha particle is shot out, and that's 2 protons, 2 neutrons. We're 2 less on the periodic chart of the elements, 2 less in atomic number, and 4 less in atomic mass. All right, in B, a neutron is unhappy, and so it's going to get rid of the electron and change back into a proton. So no change in mass because it's just an electron, but we have 1 more proton. All right, and then the last case, the happy marriage. An electron is captured, it fuses with a proton to become a neutron. We have 1 less proton and no change in mass. All right, so be able to name and briefly describe one of those. All right, let me just tell you a little bit about radiometric dating. And in that same video or in another video, I need to explain half-life. It's so easy that I think, when it finally clicks with students, they're like, what? It's so easy. Half-life is the time that it takes for half the parent material to decay to form daughter. Okay, so half-life is the time that it takes for half the parent material to decay and form daughter. So if times 0, I have 100% parent. After 1 half-life, I'll have half of that, or 50% parent. After 2 half-lives, I'll have 25% parent. All you have to do is take the percentage of parent and keep dividing it by 2 every time you have a half-life pass. Now, radiometric dating is great, but not anybody can go out and take samples to be radiometrically dated. You need to have a closed system. You can't have a leaky system. You can't have, what happens if you're measuring, because what you're doing is you're measuring the ratio of parent to daughter. And if the daughter leaks away, you'll never have a very good clock. You got to take cross checks. You never just take out 1 sample, you take a bunch of samples, and you really hope and pray that all your samples come back the same. Okay, it's a complex procedure. Typically, we throw money at the situation. We pay somebody else to do it because it takes, a lot of millions of dollars worth of machines and equipment and very specially trained scientists to do this. I don't do it. I throw money at the situation. All right, and what you actually get is a date. The radioisotope geologist or whatever does is looks at the percentage of parent, compares it to the percentage of daughter, and will give you a date based on the half-life of the parent-daughter pair. And so you'll get a date, but you know what? It's kind of funny. It's called absolute dating. There's a plus or minus. There's an error bar. And kind of the older it is, sometimes those error bars go up. Okay, but it's a radiometric date. It's pretty good, and the error's not that big. All right, it is a dependable means. It is repeatable, and there's only certain rocks you can date, and certain things, minerals you can date, but it is really a very good tool for that. All right, it's an exponential decay curve. If you guys notice in yellow, we're just going to start at 0 with 100%, and igneous rock is the best thing to date. Igneous rock, it's born when it solidifies. It goes from melted rock to solid rock. And so when it crystallizes or solidified, that starts the clock. That's time 0. And it will start with 100% parent. Now over time, the parent will break down to form daughter. And after one half-life, you're only going to have 50% parent, 50% daughter. After two half-lives, 25% parent, 75% daughter. After three half-lives, 12.5% parent, 87.5% daughter, and so on and so forth. Now you guys, if you can take 100 and divide it by 2 a bunch of times, you can figure out exactly how much parent you have. And then it should always add up to be 100, and so you can figure out exactly how much daughter you have. So that's why that closed system is so important. If the daughter leaks away, you're not going to have a proper ratio between the two. All right, now you guys, you do not have to memorize any radioisotopes and their half-lives. I will always give you those. Now, uranium-238, uranium-237, these are ones that are in the news a lot. 235 is more fuel grade. 238 is more weapons grade. They both break down to form lead, but look at 2 different isotopes of lead. Now, if you look at this, you guys, uranium is complex. It goes through a number of steps. It doesn't just go through one of those 3 steps that we learned. And uranium-238 has a half-life of 5. All right, here's just a few of the radioisotopes that we have and that we might be using. You guys don't have to memorize any of these. I will always give you the parent, the daughter, and the number of years in the half-life, and I'll even give you the percentage of parent and the percentage of daughter. So that will make your figuring out how old the different samples are pretty easily. Now, it's kind of cool. Look at uranium. There's actually 2 radioactive forms of uranium, and they both break down to form lead, but 2 different stable isotopic forms of lead. And uranium-238 has a half-life of 4.5 billion years. Okay, potassium-argon is a pretty popular one nowadays, and it has a half-life of 1.3 billion years. In potassium, if you think about it, granites typically have a lot of potassium in them. And so, dating a granite, you'd probably use a potassium-argon dating. All right, and then we talked a little bit about carbon-14. It breaks down to form nitrogen-14, and the number of years in its half-life are 5,730. Now, wow, that's not very much in geologic time, so you guys can kind of see why I don't use that. It's only useful for up to about 50,000 years. So I wouldn't use something like that. It's not old enough for my material, but if you wanted to become a historian or an archaeologist or something like that, that would probably be fine for you. All right, so again, very short half-life, used to date recent events, and again, recent geologically, because it could be in the last 50,000 years. And, historians like to date it. If you thought you found the ancient city of Troy and you found burned wooden pillars, you might actually date the wood and see, what does it date to? Or you find a Viking ship. I know one geologist who does use carbon-14, and he actually studies recent movement on the San Andreas Fault. So movement in the last 50,000 years along the San Andreas Fault. But, I don't use it. My stuff's too old for this.